Hello students, you all are warmly welcome to our YouTube channel, Chemistry Teacher. It's we are going to present you another lesson belong to organic chemistry. It's alkyl halides that we are going to talk here about. Students, hope you could remember that earlier lessons we used to talk about alkanes, alkenes, alkynes, benzene and its derivatives. Those all contained carbon and hydrogen only. Therefore, we name them as hydrocarbons. Then, stepping ahead, we are going to find out what would happen when another different atom rather than carbon and hydrogen only you have there within the molecule. It's our first effort is finding out when it is a halogen atom. So, it's halogenated hydrocarbons, or you would call them alkyl halides. Then further, we would be talking about later on. It's when you have oxygen atoms there, when you have nitrogen atoms there as well. So students, let's first find out what would it be when it's a halogen atom. So it's by the name, it's alkyl. I could denote the term alkyl with the letter R. I could symbolize alkyl with the letter R. It stands for methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, decyl. Such alkyl groups that we have already looked at. Then halides could be symbolized with the letter X. This X could be a fluorine, a chlorine, a bromine, or iodine, any such. Then students, those are the alkyl halides. So, for an example, it's when you have, it's the methyl group standing for alkyl group, and when you have, it's a chlorine atom, the halogen. So, when you have two carbon, we call it ethyl, the group, alkyl group, with the alkyl group ethyl. When you have the halogen atom bromine there, it's alkyl chloride here, alkyl bromide there. So earlier we had such a situation that carbon got 4 single bonds, but all the bonds were with hydrogen atoms. It was the first alkane. It is methane. So what's the difference between methane and methyl chloride? Why is that so important? Why is that we are having another different topic, unit or different lesson standing for this? Not unit, different lesson standing for this. Students, it's between carbon and hydrogen you have an electronegativity difference. Carbon is 2.5, hydrogen is 2.1. So all bonds are having the same electronegativity difference. So then carbon would be the more electronegative species there. Then though it's not a very high electronegativity difference, you would expect some dipoles as slight positive, slight negative. Let me call it. It's slight negative, slight positive, slight negative, slight positive, slight negative, slight positive, slight negative, slight positive. So within hydrocarbons, when you get such electronegativity differences, as well as therefore some dipoles, the net result would be cancelled off. Though you have dipoles there, their dipole moment would be 0, for the reason they arrange in the space symmetrically. They are having 4 bonds, it's tetrahedral arrangement, geometry you get. Then what's the difference? What's the difference here you have? Students, here also you have this being slight negative, slight positive, slight negative, slight positive, slight positive, slight negative. But when you compare this, here 2.5, let's call it the electronegativity value, but it depends on the compound. Though it's the same element, it's compound to compound based on its valency, hybridization, the charge it's carrying, and such things. It's it's going to vary the electronegativity of same element. But generally we call it 2.5, the value given on carbon. Then it is 3.0, the value given on chlorine. So there also you have an electronegativity difference of 0.5. But now difference is working as this is more electronegative, this is less electronegative compared to this one. Therefore there is not a symmetric one. Those dipoles were not symmetrically distributed, therefore it's not going to be zero, the dipole moment. You could expect some sort of polar character here. Within alkyl halides, that's the difference compared to alkanes you have. Hope you could remember regarding alkanes. When you find out their reactions that alkanes exhibit, it's not much reactions alkanes involved in. It's hope you could remember, in the presence of UV radiation only, it was a halogen substitution reaction took place. That also was a free radical substitution reaction. Then other than that, its alkanes do not involve in such conversion steps. You could talk about its combustion, but we are not taking alkanes combustion or those organic compounds combustion in conversion steps much. Then students, therefore, its alkanes quite remain like inert substances within organic chemistry, but it's not fully true. It involved in some reactions like halogen substitution in the presence of UV light. Anyway, compared to alkanes, for this reason, it exhibits some sort of polar character. It involves in some reactions than alkanes. That's the difference of having a halogen atom to the position of hydrogen atom. So it's going to express different chemical properties, chemical characteristic behavior, as well as physical characteristic behavior. So compared to alkanes, these alkyl halides are some sort of polar substances. You could find some sort of polarity there. Though they are polar substances, these alkyl halides, they can't form hydrogen bonding with some other molecules like water molecules or such. And they can't form hydrogen bonding. Hydrogen bonding means it's a strong permanent dipole. Within the permanent dipole family, it's the strongest. So they can't form such strong permanent dipole, or it's called hydrogen bonding with other molecules as well as with their own molecules, intermolecular hydrogen bonding. They can't form. So therefore, though they are slightly polar, their polarity is not enough to form hydrogen bonding with other molecules, with water. Therefore, they are not water soluble. Though they are slightly polar, they are not water soluble. So then when we check for their reactivity, there are some reactions these alkyl halides exhibit. Those are showing, those involved in. So if we are going to talk about their reactions soon, then before talking about their reactions, we need to see clearly what's the reason of this reactivity. Which kind of reasons are cause this reactivity. So our effort is now to find it out their reactivity. So students, basically their reactivity is given by this bond. So this bond is having a kind of difference in electronegativity difference. It is slight negative here, slight positive here. So it's different, the electronegativity difference of other bonding. So therefore, this carbon remains as slight positive center, and this halogen atom here, the chlorine atom, remains as a slight negative center. It's slight negative, slight positive. They are dipoles. you could find such dipoles. So then on this carbon you could find electron deficient site. Electron deficient site. For the reason it's having slight positive dipole. Then on this chlorine, you could halogen atom, you could find electron, excess electron. Means it's not many electron, excess one electron. It's just slightly, its electron density is greater than normal situation. Therefore, it's a slightly negative N, slightly positive N, slightly negative N. Those are what you get there within the bond. So this makes, when this carbon find any other site or any other species carrying electrons, especially lone pairs, negative charges with some species, let's say. So when it finds some coming with more electrons, coming with lone pairs, then this would get attracted towards that and get attached there. So that's what it's possible. Therefore, it provides a site for those who come with electrons. Those who come with electrons, they are seeking for positive sites. Those who come with electrons, therefore, are calling positive lovers or positive sites lovers. Positive sites you could find within nuclei of atoms. Are those love nuclei? Those are nucleus or nuclei lovers. Those are nucleophiles. Those who like positiveness are nucleophiles. Then this slight positive center or having slight positive charge on carbon, it invites those nucleophiles to get attracted towards that and do something on that. That's what the difference between normal hydrocarbon and these alkyl halides. Those alkyl halides, let's find it here. Students, you get here a slight negative, slight positive. Two dipoles. Therefore, this could participate in reactions with nucleophiles. This could invite those nucleophiles as to come and get attached. Then some reactions could take place. Then, if it is something like another new species come and attacks there and get attached there, then this halogen has to leave the molecule. So its poor halogen would be leaving the molecule as Cl minus, Br minus. It won't be leaving just with empty hands. It would be taking both electrons there in the bond. Both electrons there in the bond. It would be taking one extra electron from this carbon and leaving. Therefore, those could leave as Cl minus, Br minus. Another important feature, character of these halogens is they could leave as X minus, halide ions. So they could let those others to come and get attached and leave as X minus. They are good at that. So we call them, they are good leaving group. Then students, it's the reactions, the reactivity of these alkyl halides basically depends on the halogen atoms leaving ability. Then it's you could find within this category alkyl halides, their reactivity being dependent on the relative ability of their leaving as halide ions. Okay students, it's now we are going to find out their relative leaving ability of those alkyl halides. Let's talk about different alkyl halides. What are the different alkyl halides? So I'm not going to change the halogen atoms. Let's use one halogen. Let's use chlorine atom. Okay, so saying different alkyl halides, I'm going to change those alkyl groups type. So students, it's when you have chlorine group attached on this, it's a methyl group. So it does not have 2 or 3 alkyl groups on this carbon atom. That you have this halogen atom straightly attached. So if this carbon is carrying further alkyl groups as 2 alkyl groups, then we call it secondary alkyl halides. So if it is carrying 3 alkyl groups, so we call it's a tertiary alkyl halide. So this does not belong to secondary or tertiary. So it is a primary alkyl halide. Then students, it's when we have a methyl group there, then this also is not carrying more than one alkyl group. Therefore, that also belongs to primary type, primary alkyl halide. But look at this. It's when you have chlorine and attached to this carbon having 2 alkyl groups. It's a secondary alkyl halide. So it's this carbon carrying the chlorine atom is having 3 of alkyl groups. What would it be when it is 3 of alkyl groups? Students, it's been called tertiary alkyl halides. Okay, it's when you have less than 2, it's primary. It's either no alkyl groups or 1 alkyl group is possible. It's primary alkyl halides. So when you have 2 alkyl groups, it's secondary alkyl halides. When you have 3 alkyl groups, it's tertiary alkyl halides. You have such different alkyl halides being possible. Then I am going to make it further different. Students, let's talk about an alkyl. A carbon-carbon double bond there. So they carry a double bond there. If you have a chlorine here, we call it vinyl chloride. It's the starting material of polyvinyl chloride synthesis, PVC. Okay, anyway, it is another alkyl halide. It is vinyl chloride, so it's different from others. Then I will take another such as when you have a carbon-carbon double bond and here another carbon carrying the chlorine. It's not straightly on the carbon-carbon double bond you have now, the halogen atom. It's on the atom here. So this is another different one. Then taking another different, shall we talk about benzene ring? Okay, students, when you have a benzene ring, if it's one hydrogen is substituted by a halogen atom, here chlorine atom, it's we call chlorobenzene. Let's take chlorobenzene as well. So then further I am going to make it different as it's on one carbon next to benzene is having the chlorine atom. So we call it benzene. This part is called benzene, benzyl chloride. Okay. So it's now we are going to find it out. Their relative ability to leave the molecule. So we found out that there is an electronegativity difference that makes this carbon slightly positive, this chlorine slightly negative. So within all these you could find that. Then for that reason, that chlorine atom here would be able to leave the molecule, letting another party to get attached here, giving a chance to another one. This chlorine atom could leave the molecule. So it's a reaction. So therefore, these alkyl halides would involve in such reactions. But it's now we are going to find it out whether all the alkyl halides equally could participate in such reactions. We still don't know what these reactions these alkyl halides involved in. So we are going to find them out. We are going to find out these alkyl halides reactions soon. But when we do that, it would be very, very important, this knowledge of their leaving ability, for us to understand what's having there regarding those reactions. There are 2 such reactions we are going to find out. It's nucleophile substitution as well as elimination. Such reactions these alkyl halides exhibit. Let's find them out soon. But we can't understand when we have those reactions, if we do not know how these halogen atoms segregate, how could they differently leave, or their different leaving ability. When I say different leaving ability, by that word or by that idea, within that idea, it's you might have got that. So they are leaving differently. That's why we are talking of these molecules, all the molecules. So it's not equally these chlorine atoms within these all molecules got the talent to leave the molecule. So the one who could easily leave would let others to react with the molecule. So would be more reactive than others. Okay. Then let's find it out how they leave differently. Okay. So on that purpose, I'm going to number, or let's give letters on them. It is A, B, C, D. I'm randomly giving E, F, G, H. So we are going to first find it out how they gonna be differently leave the molecule chlorine atom. So students, if you consider the one here we are having as A, when the methyl chloride is there, when it is having this chlorine be left, how does it leave? This chlorine leaves as Cl minus. When it leaves Cl minus, it results a cation there. What's the cation it results? It's the carbocation. It results here. So it leaves as Cl minus. Then students, this is the carbocation form there. So in that manner, I could talk about all the carbocations could be formed by these all leaving of halogen atoms. Shall I? So if I then if I write then those carbocations close by each, it's representing this. I could write the carbocation here, but I have already got. Then students, when it is not methyl but ethyl, the group, how could it be? When it is CH3 another, it is not this molecule, now it is this molecule, B1. So when you have chlorine in B leaving, so it would be a carbocation formed like this. So it is ethyl carbocation, CH3, CH, H plus here. So and chlorine and chloride ion. So then when it is about this chlorine leaving, you would accordingly get the carbocation formed as here it's a CH3 representing these two. So this is a H and this is a plus, and there will be a Cl minus. So then I'm erasing this. So hope you have got the idea. So students, it's when you have this chlorine leaving, so it would take these two electrons in the bonding with it, so making it Cl minus. Then you get this carbocation CH3, it's a positive charge there on that carbon. Then students, similarly, when you talk about this substance, this is a vinyl chloride, right? So it's you would get this resulting when it leaves as Cl minus. If it leaves, then you would get a positive charge here. Similarly, here you get it's a double bond now. You had a double bond here, so you have this being left. So it's a CH2. It's a plus charge there. You get. Then students here, let's make it leave. Okay, if it leaves, then what you get there? The positive charge on carbon here on benzene. So if you, okay, let me erase these dot lines. If you let this chlorine to leave, then what you get there? is, you get a benzene ring, then you have CH2, it's CH2, and after leaving of this Cl as Cl minus, what you get is benzyl carbon cation. These are the carbon cations you get standing for A, B, C, D, E, F, G, H. Okay. So it's not involving, not interfering in their leaving. It's we let them leave as they want. Okay. So then students, let's find it out what would happen next. What would happen next is there are relative stabilities of the formed carbon cation is now in our concern. Is now we are going to find it out. Think it like this. If you have alkyl halides, any such, then when this chlorine is willing to leave, it would be leaving as Cl minus. It would be leaving as Cl minus. It would be leaving as Cl minus, resulting in a positive charge on the carbon. 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 Then positive charge after leaving, after it's leaving, there would be a positive charge resulting on the carbon. So positive charge on the carbon. Positive charge on the carbon. Positive charge on the carbon. Then when you find these cations, those cations written in red, when you find them differently stable, if they are not equally stable, these cations. So anyhow, still we don't know how they are differently stable, which one is more stable than other. Okay, we still have not talked about. You might feel like this would be more stable than other or something like that. If they are differently stable, how this leaving would happen? Could you imagine? Now you have a chlorine. Now you have a chlorine on carbon atom attached with a single bond. It's a covalent bond. This chlorine is thinking on leaving. This chlorine would be leaving as Cl minus at the next time. When it leaves, it results a cation. When it leaves, it results a positive charge species. So, if you find these positively charged species being differently stable, then students, their leaving also would be affected there. They would be leaving differently. How differently? If you are leaving your home, if you feel it like after your leaving, the home's status or the home would be unstable. Means thieves could enter the home and they could rob things there. So then you would be thinking again whether to leave or not. Okay. So similarly, if this chlorine atom feels like after my leaving, this molecule being a cation would be unstable, then that idea, that attitude would make kind of that leaving as it would discourage the leaving. It would make the leaving kind of not that much. So it would discourage the leaving. So if it feels like after my leaving, this poor molecule would become unstable, I better rather stay there. So not leaving. Okay, it's like that. If you feel like, okay, my door lock is not functioning well, so windows are also not having locks, so I don't have a CCTV system there in my home, at my home, so it's not a well kind of secured gate or security system I have. I don't have even a door there, so I better stay there at home. I will go tomorrow or another day, not today. So because it's highly unstable, the condition here. Thinking that you would stay at home. In the same way, Students, this Cl, if it feels like highly unstable after it's leaving, it would not be leaving that hurriedly. There would not be such a hurry to leave. Therefore, its leaving would be discouraged by such an unstable situation after the leave. So, therefore, if we compare these cations formed, their relative stabilities, if we find some are being stable comparatively than others, their leaving would be more encouraged. Others' leaving would be discouraged. That's what the point is. Hope you could understand. It's very simple. Again, these halogen atoms, this chlorine atom would be leaving well if it feels after its leaving the formed carbocation is not that affected, not highly unstable. So if it finds it's a stable carbocation it's going to form, then it would be leaving easy. If it finds it's unstable carbocation going to be formed, its leaving would not be that easy. That's the point. Okay. So therefore, students, if we could compare these cations' relative stabilities, then we could find it out. We could predict it whether it would leave easily or not. So let's first consider these four A, B, C, D, because they all are simple alkyl halides. These also are simple, but let's first consider these four in the comparison first. So students, you have just 3 of H's only on the carbocation. Then you have one methyl group, alkyl group. Alkyl groups are electro-repelling groups. It pushes electron towards the carbon. That's what alkyl groups are famous at. Okay, alkyl groups are electro-repelling groups. They repel electrons through the sigma bonding that they have got attached with. So then towards this carbon it's giving electrons. It's not fully giving. It's this electron in the bonding would be pushing towards that carbon. So the electron density there towards that carbon would get increased. So it would be increased by one alkyl group. So there is no such alkyl group. Therefore, this I need to say this as well. Students, when you find charges there on atoms, they are unstable. Then compared to when you do not have any charge. When an atom is neutral, electrically neutral, it would be stable than when the same atom is carrying either negative charge or positive charge. Therefore, the comparison is made. They all are having 1 plus charge within those cations. The comparison is made whether that plus charge is neutralized or is stabilized by giving electrons towards that, is stabilized, lowering its positivity, neutralizing its positivity. It might not be completely, but pushing electron also is a kind of support. So this methyl group is supporting on this carbocation, that positive charge, increasing the electron density. It's not giving one electron there. It's just pushing electrons through the sigma bonding. So the electron density is quite close by this carbon is quite increased by this methyl, this alkyl group, repelling electrons. Okay. So therefore, this is more stable than this. In the comparison, I would say it is B is more, the carbocation formed by B is more stable than A. Okay. Then this you could now easily understand. When you compare this carbocation, then students, it's having 2 alkyl groups. Therefore, there are 2 electro-repelling alkyl groups. So the secondary carbocation here would be more stable than primary carbocation. Therefore, I'm going to say the carbocation formed by C, right? C going to be more stable than carbocation formed by B. Both these belongs to the primary, but this is having 1 alkyl group. Therefore, it's better than this having no alkyl groups. Then students, when you compare it with this, it's a tertiary carbocation. So it's having three such alkyl groups giving electrons. So it would be more stable than even this. So it's, I could say, D is the best out of those four. Okay, that's the comparison made between these. Okay, then it's my effort here to find out how is the stability of the carbocation formed by this. This is the carbocation. Then students, it's when you have a positive charge on a carbon with a double bond or triple bond, it's highly unstable. Further, when you have a positive charge on a carbon of benzene, it's unstable. It's very highly unstable. Why is that? So those pi electron systems, would be disturbed by having no positive charges there. Mostly, at most of the time, those pi electron systems would delocalize. So those would be disturbed by having no positive charges there. Therefore, on a carbon-carbon double bond or triple bond or a benzene ring, having a positive charge would be unstable. So it's therefore this is unstable, and it's in the same as the sense this is unstable. But I'm not just going to say it's unstable only. I'm going to show you why is it unstable. Why is that unstable there in that way? So students, I'm going to show you now that why is that this is having a positive charge is unstable. Leaving of this chlorine there as chlorine minus is difficult. So given that, I could tell you this. When you have this vinyl chloride, this chlorine is carrying 3 lone pairs. Then it's 2 H's and 1 H there. Then students, we could talk about a resonance structure, as this lone pair could be given here to form a pi bond. Then this pi bond could be broken here, giving a resonance structure. That system itself could resonate. So what you get next is, now the pi bond here is no longer existing. You have these 2 H's, and these 2 electrons were there in the pi bond is now on this carbon. It's negatively charged now with the extra electron, additional electron given by this carbon was there in the pi bond. So it's now you get CCl double bond. So it's a negative bond, therefore it's a plus charge you get. So it's a hydrogen. So likewise, it could resonate. It could form 2 resonance structures. So students, this system which could resonate would be disturbed after this leaving, after formation of plus charge or cation, giving a positive charge on it. It's not only that. If you are thinking of this chlorines leaving, if you check this resonance structure, you could easily see it's having a carbon chlorine double bond. So when you consider the leaving of this chlorine, it's just a single bond got to be broken. So now it's a double bond to be broken. Breakage of double bond is not that easy as breakage of a single bond. If it was about leaving here, leaving here, leaving here and leaving here, at all those times they have got a carbon chlorine single bonds. But when you consider this resonance structure, you have carbon chlorine double bond. So you could argue like this is a resonance structure only. It's both of these are possible at the same time. Yeah. Then students, when you consider their resonance hybrid, then also you could expect partial double bond character between carbon and chlorine. Therefore, the breakage, cleavage of that CCl double bond, or let's say partial double bond, would be difficult. Therefore, normally this chlorine does not leave. Leaving of this chlorine not going to happen. Okay, so therefore it's very very weak. Its leaving is very very discouraged. What's that? It's E. E won't be easily leaving. So it's very difficult you to remove, you to break that bond. It's a double bond character itself. Hope you could understand. So therefore its leaving is not easy, at least when you compare it with methyl chloride. It's very difficult leaving of that chlorine as Cl minus. Okay, so then it was our concern there with this chlorine. So shall we look at this structure? Okay, so students, I'm now going to consider the structure G. It is chlorobenzene. After leaving of this Cl as Cl minus, you get on a plus charge on benzene. As I have already told you, having a positive charge on benzene ring is unstable, therefore it's not going to leave AB. Okay, so then how difficult it is? We have already found out leaving of this chlorine is difficult. Is that equally difficult or further difficult than of that? Is now we are going to find it out. Then students, it's when you have this chlorine there, that chlorine is having 3 lone pairs. It could form resonance structures. We have already considered the resonation of chlorobenzene. In that topic, finding out the impact done by the substituted group on benzene, we found out the resonation of chlorobenzene. There, chlorobenzene's chlorine gave the lone pair towards benzene ring and formed 5 resonance structures. Okay, so I'm going to show it, those 5 resonance structures. Students, if I draw it in this manner, this form, this is chlorobenzene. So this lone pair will be given towards that benzene ring. This pi bond will be broken on carbon here, forming a resonance structure. So the next resonance structure is having a double bond here between carbon of benzene and chlorine. So it's 2 lone pairs only. Now you have, it's a positive charge you have. Then it's 2 electrons there you have, and you still have those 2 pi bonds. Then students, it's further use this lone pair here. We'll symbolize it in a different color. So this lone pair here will form a pi bond here, and this pi bond will be broken on that carbon. So students, what you get is you have this double bond still there, and you have the positive charge and 2 lone pairs on chlorine. Then students, you have a new pi bond being formed there, and this pi bond still there. You have those 2 electrons were there in the pi bond come here, and now it's a lone pair with a negative charge. Okay, at the next time, it's going to use that lone pair as to form a pi bond here. Then this pi bond would be broken on this carbon, giving you another resonance structure. Let me draw that. It's students, you get still a double bond here, and you have still 2 lone pairs. It's a positive charge. You have this pi bond still. Then you have a new pi bond being formed. After breaking of this pi bond there with the 2 electrons, it's a lone pair. Then the students, final structure I'm going to draw. I could break it here as to form a pi bond and break it here. Then again we are going to have the similar structure having 3 pi bonds there, and just a chlorine atom with its 3 lone pairs. So there are 5 resonance structures formed. So if you let this chlorine leave as chlorine minus, then you get this a plus charge of benzene. Then all these 5 resonance structures would not all those 5 resonance structures would not be formed. Those 5 resonance structures are hindered. So it was 2 resonance structures formed by this were hindered. That's why it was not allowed, leaving of this. Now what? Now it is 5 resonance structures, formation of 5 resonance structures would be blocked. Therefore, it's another thing is when you compare it with those 2 resonance structures, it is out of 5. In 3 resonance structures, you get benzene and chlorine double bond. Therefore, leaving or breaking of that would be very, very difficult. Then student, it would be highly difficult to make it leave that chlorine on benzene. Therefore, this carbocation on benzene would be highly unstable. It would be highly unstable. Hope you have got it. Students, therefore, the place I will draw that letter G is here. It's the most difficult one out of those so far we have looked at. Okay, then there are another 2 to be discussed. One is this. So when you let this chlorine leave, you get this cation being formed. Then students, this cation could resonate. Then let me draw those resonance structures. You could get a double bond here. It's a positive charge here. So it could resonate in the way like this pi bond could be broken here, forming a new pi bond. Then it's you would get 1, 2, 3. Now the new pi bond formed here, and you have still these atoms. So this is the positive charge. Now it appears here. It's forming resonance structures. There are 2 resonance structures formed by this intermediate one, cation. So far we have found out tertiary alkyl, tertiary carbocation being the most stable out of these is the D. Then students, it was just for the reason these methyl groups they repel or push electrons towards the carbocation, increasing the electron density close by the carbocation, letting carbocation's positiveness to neutralize. Okay. But anyway, it's good. Anyway, it is not neutralized fully. The positive charge still there, but compared to that, it's better. But when you compare it with this, you had a positive charge once, and now the positive charge is no longer there. It has shifted to on this carbon to this carbon. It's like this carbon is in a trouble, means it's having very, very kind of unstable its positive charge. So this carbon is telling, give me your positive charge to me and you take a rest. So then it would be highly stable now. So after giving the positive, passing the positive charge here, so it delocalizes the positive charge. This delocalization of positive charge makes it highly stable. So it's no longer the positive charge you have there. So compared to that, this is better. If any carbocation, any cation could transfer or could delocalize its positive charge within the molecule throughout the chain, then it would be highly stable. It would be very, very stable. Then even this tertiary carbocation, this carbocation form would be stable. Therefore, this chlorine would, its leaving would be very easy. It would easily leave. It knows that though I leave, it's after my leave, the formed cation anyway could survive. It could be stabilized, forming these resonance structures. Therefore, its leaving is encouraged. Therefore, students, it's the more stable carbocation form so far out of these. It's therefore you could find its leaving being more easy than even D. Is the substance F, right? Okay. Now it's one only we are having. It's this. This is benzyl carbocation. Then we might be able to have an idea. If it also would form resonance structures, it also would be stabilized. The carbocation's positive charge then would be delocalized. Then it would be more stable. Then it's just about the number of resonance structures formed. If its number of resonance structures is greater than this, here it formed two resonance structures. If this could form further more resonance structures, it would be more stable, the carbocation form, so it would be so easily going. That's all. So let me explain that as well. Students, you would have, when that benzene, it's benzyl, when that benzyl, it's carbocation here. So when it starts forming resonance structures, this carbon would be broken towards this carbon, forming a new carbon there. So it's what you get here is a structure like this. It's a double bond now you have. So its positive charge is no longer existing. So you could find a positive charge being appearing there. So students, these pi bonds are still there. Then this pi bond would be broken there. So it's what you get next is another resonance structure. Still you have the double bond with two H's on carbon. So there's a new pi bond formed there. Then this pi bond was there, so it's a positive charge would be there on that carbon. So then what would next happen is this pi bond would be broken here, forming a new resonance structure. What you get next is another resonance structure with this pi bond still there. A new pi bond being formed is a positive charge. It's a double bond still. So you have this. Then last one is when this pi bond is broken here, so it ends, means it gives a similar structure as you have got at the very first. So students, you get another this kind of one. So there are 5 of resonance structures were being formed. Therefore, this chlorine could easily leave, because after leaving of that, the form cation is stabilized by delocalization, forming 5 resonance structures. With increase of number of resonance structures, the stability also would get increased. Then hope you could understand this all. Therefore, I could place, erasing this, I could place that benzyl chloride to the top position. It's the best one. It's the best one of relative leaving ability. It's the H. That's how you get. Okay, let me erase those all and draw them again from the beginning. Then students, I could place what? At the least, I could place chlorobenzene. Then next one is vinyl chloride. They won't leave so easily. Vinyl chloride. So they are clear that side as well. Then students, you could find next those primary alkyl halides. First methyl chloride, then ethyl chloride. So what you would get next is secondary alkyl halides. It's this CH3 Cl. So it's 2-chloropropane. Then it's the tertiary one. CH3, 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 Cl. 2-chloro-2-methylpropane. Next one is, you could find CH2 double bond CH, CH2 Cl. It could leave easily. Okay, next one is, the last one is benzyl chloride, CH2 Cl. So in this order you would find their chlorine atoms leaving. So then their reactivity also would be affected. So their reactivity, when you decide, you need to know the way, the ability of their relative leaving. So students, we are going to find out more details there regarding their reactivity and such stuff, their physical chemical properties regarding those alkyl halides. After this, you need to know their relative leaving abilities. Therefore, we are going to use that in their relative reactivities. Okay, so in our next video, we are going to consider about their reactions of those alkyl halides. Okay students, goodbye.